Welcome everyone to the second talk of today. So let me start by introducing our speaker. Professor Gukov obtained his PhD in 2001 from Princeton University under the supervision of Professor Edward Whedon. He then was a long-term prize fellow of Clay Mathematics Institute at Harvard University and then a member of School of Mathematics in Institute of Advanced Study in Princeton. And since 2007, he was a member since 2007, he has been a professor of theoretical physics and mathematics at California Institute of Technology. And from 2010, he was also been an external scientific member at Max Planck Institute of Mathematics in Bonn. Professor Gukov has made numerous groundbreaking contributions in string theory, quantum field theory, geometry, and topology, where in particular he used resurgence techniques to obtain non-trivial new results. Today, Professor Gukov will give us an overview talk about the use of resurgent asymptotics in these fields. And before we start, let me remind you that in principle, you can ask questions using your audio, and then you're actually also encouraged to use your video at the same time. But then you have to know that you will be recorded. If you don't want to be recorded, then you can ask questions in chat. And if you want to ask questions during a talk, you can also raise a hand. And at the very end, after kind of a more formal part of the talk will be finished, the recording will be stopped and you can ask more kind of informal questions without being recorded. So please, Sergei, you can go ahead.
Thank you, Pavel, for very kind words and kind introduction. I also want to thank all the organizers of this program, first of all, for their effort in making it happen, for putting it all together, and of course also for giving me this honor to give the overview talk, this opportunity. I have to say that, in my opinion, such overview talks are best given by founding fathers of the subject, by pioneers of the field. And I'm certainly not one of them. So my first disclaimer is that I'm not really a founding father, and therefore the only benefit of me giving this talk, I guess, is that it will present a sort of outside opinion as an outsider or user of resurgence, what the subject looks like. And the organizers asked me to give an overview of how resurgence is used in quantum field theory and string theory. So this gave me an opportunity to reflect a little bit on what has happened and study the history of interaction of resurgence with quantum field theory and string theory. So today I want to invite you all on this journey with me to see how resurgence influenced quantum field theory and string theory, and even talk a little bit about the history of the subject. So when I work with students, I usually encourage them to study pretty much every single paper that exists on a topic that they want to explore, revolutionize, or make contribution to. So I decided to follow my own advice and basically study every single paper that exists on resurgence and quantum field theory. So simple way to do it is to go to this InspireHab website, which is a version of arXiv that virtually has pretty much every single paper on quantum field theory. So you can be assured that if there are papers on quantum field theory or string theory, this is extremely efficient database that captures those papers. So therefore, I did the most obvious experiment. I typed find all papers which have resurgence, the word resurgence in the title, just to see what the history looks like. After all, before I start an overview, I want to know what we're dealing with. How big is the subject, and what's the scope, and so on. And obvious search returned only 73 papers. So this is actually a manageable amount. So I was a little bit worried whether it means I have to read thousands of papers or hundreds of papers. So it basically came about on the order of 100. So that's one nice surprise. It's kind of manageable and makes my job a little easier. And also another thing that I discovered by doing the simple experiment is that it has a clear starting point. So now is 2021, and I want to draw your attention that this search or papers that have mentioned resurgence in the title actually start in 2011, which is exactly 10 years ago. So this gave me a kind of nice motto for preparation for this talk, 100 papers during past 10 years. So it's also useful sometimes to go and see how it started. So in the very end of the slide, I show you the very first paper, the one from 2011, which has the word resurgence in the title. And it's a paper by Ines, Ricardo, and Marcel on resurgence in string theory. And already in that paper, they use very advanced techniques from resurgence, and there are many cool results. For example, they found new non-perturbative sectors in topological string theory. So these are some things that I'll mention throughout the talk. And of course, I'm not going to review all of the 73 or roughly 100 papers that I read. If I try to do that, it would only allow me to spend 30 seconds per paper, and that wouldn't be useful at all. So just like in the previous talk, I'll try to give you some of the illustrative examples and mention maybe different areas, or try to group these search results in categories to draw lessons on where and how this interaction between resurgence and quantum field theory influenced our understanding. But I also want to pose this question in a way that allows us to reflect and think about where we go next. In particular, I want to look through this experience and identify what are the next opportunities. In other words, is this kind of field which is already very mature and had many home runs in the past, or are we likely to see many more exciting results and home runs are awaiting us in the future? So these are kind of questions that I'll try to extract from research that I've done for this talk. So
may I have a quick remark concerning this history? I think the founding father of resurgence in quantum, in physics in general, not in math, was Midhat Unsal. And it was earlier than 2011. And if you look into the literature carefully, you will come to this answer too.
I certainly did.
I remember,
in fact,
I remember
yes.
very well his first paper and how he introduced into physics this Kaye mathematician, the mathematician, and his first paper, second paper, and the followers came after him.
Misha, I completely agree with you. In fact, his name will be prominently mentioned in later parts. Of course, I totally agree with your conclusion. And as a participant of resurgence community, it's not hard to notice influence and indeed founding fathership of many people, Gerald Dunn, Midhat Unsal, and of course, I didn't mean to say here that I didn't give any names for founding fathers. I just said that I'm not the one when I started this talk. But even with this slide, of course, there are many caveats, and you pointed out one of them. So I'll try to, again, be accurate, but also, if we ask when is resurgence most influenced quantum field theory and string theory, I think it is kind of fair to say that it's being very active in the past 10 years. So that's part of the reason why, just to give myself some manageable task, I decided to mostly focus on developments in the past 10 years. But of course, there are many papers I had to read also from earlier times. So that's why my basis or foundation is not just 73 papers mentioned here, but actually more than 100. And in the next slide, I'll show you a couple of more.
Okay, thank you.
Good enough answer?
Yeah, thank you.
Of course. So yeah, feel free to make comments, but again, the remark about founding fathers was mainly to say that I'm not the one. In fact, part of the slide is also to illustrate that the trajectory of this field is growing. So that's one takeaway, and in particular, I'll spill the beans a little bit that, of course, I expect many more exciting developments to come in the future. So I want to think about derivative in this slide. Now, to preempt more comments along the lines that Misha just made, of course, I want to point out that there is an obvious caveat in the search. So here I focus, or did the search just looking for word resurgence in a title. And you could argue, of course, that if someone finds resurgence very important in their work, then they would put it in the title. But of course, it's possible that it didn't make it into a title. And so I did a couple of other experiments. For instance, another experiment is to look for papers which have the word resurgent in the title. And here you see actually something very similar, that a lot of developments, a lot of activity is concentrated in the last 10-year period, which gives me a nice round number to talk about. And there are a couple of early papers which mention resurgent in the title back in early 2000s, so it's still not too far from this 10-year period. And they deal with field theory amplitudes and instantons and quantum mechanics, respectively. So these are the two papers in the bottom of the screen, which are these two outliers that go 2002 and 2004. So this is just to illustrate that I did a little bit broader search, and here this order of magnitude of work is about 30 papers. So that's a nice contribution to the previous 70, which makes it about 100. But again, of course, this is, I didn't stop here. This is way too naive. So I decided to go to a different database, namely arXiv, and look for papers which have resurgence in the abstract, anywhere basically in the title and abstract. So this is a little bit more inclusive. And this returned 127 papers total, a little bit over 100. And in fact, it returned some references which go back to 90s. And here I said to myself, oh, this is interesting sign. So maybe indeed I should do a broader search. But for instance, these two first papers, which go spill into the 90s, do mention resurgence in the abstract, but the meaning of the word resurgence has nothing to do with the way it's used in our program. In particular, it just means that some subject came back, and one paper was on supersymmetry breaking, which made me first very excited because I thought, oh my gosh, there is application of resurgence to supersymmetry breaking, and that sounds super cool. But unfortunately, it wasn't resurgence in the mathematical sense, and also the use of resurgence in this paper on the renormalization group used it in a different sense. So I did many more experiments. I'm not going to bore you with how I try to identify the history. And again, of course, I read many references even in this roughly 100 papers that talk about resurgence explicitly. So I try to do fairly inclusive search, and then reflect on what has happened, how it influenced our developments, and so on.
Could I, Michael Berry here, may I just interject one little comment? I don't want to slow you down, but again, concerning history, I'm a little bit surprised that you don't mention the person who gave the name to the subject, namely Jean Cal. Well, that was the 1980s, but he acknowledged that the first person known to him who had a fundamental result in the fact that the high orders of each of the asymptotic expansions associated with a given function contain coded into them, because of analyticity, information about all of the other series. So each one contains all the others. And that goes back to Dingle in the 1960s. Now, it's a curious historical fact that when I was Dingle's research student in 1962, he told me that he was studying universality in high orders of divergent series that occur in physics because he had spent a year in California with Keith Bruckner, and he dreamed that ultimately there will be applications in many-body physics and quantum field theory, which of course he never did. But he did find the first explicit resurgence formulas. So, you know, the history goes back a long way.
I totally agree. In fact, thank you for this remark. I didn't actually know about this particular fact. I'm glad that you made it. Thank you. Thank you, Sir Michael. And later on, I'll show you many other references, in fact, which mention resurgence back in 90s and 80s. So it does go back. Again, I try to show you here very well-defined control experiment where we simply search papers by the mention of the word resurgence and analyze the small cross-section of the data. So I completely agree that there are papers which do mention resurgence even in 90s, but at least a result of this experiment is that they don't make it prominent enough as far as interaction with quantum field theory goes. And interaction with quantum field theory, where we see this prominent mention of both resurgence and QFT techniques, is reasonably well localized in the past 10 years. And indeed, I agree with earlier comment that people like Mithat Unsel and Gerald Dunn, and in fact Misha Schiffman himself, are some of the founding fathers and people who propelled this interaction. So therefore, I want to, like I say, focus mostly on what we learned in the past 10 years. If you wish, this is mostly to make my job self-contained and reasonable, because I only have an hour and it's really hard to review even this 100 papers. And my main goal is to ask a question: what do we learn and what does it do for physics? Namely, what is the role of resurgence in quantum field theory? And again, the main results are fairly recent, so that makes my job reasonably self-contained. And I want to compare resurgence, and I'll come back to this, to a technique, and I was thinking about what would be the best comparison. So one of the examples I could think of, I'm not sure if it's the best, is a replica trick. So in other words, resurgence is a method, and it's a technique that can be applied to many different systems, so that's a good thing. And here is, for comparison, the history of use of replica trick. Again, of course, it's very naive, and there are many papers that don't even mention the word replica in a title, but you can see that it has a bit longer history. And my hope, or one of the outcomes of this talk, is going to be that I hope resurgence will play a role similar to replica trick and will have a long-lasting life in quantum field theory. So one takeaway, which again you can do even from this very simple objective controlled experiment of doing the searches, is you quickly see that the role is growing. So one way to characterize the role of resurgence in quantum field theory at a very basic level is to see that it's increasing, it's going up. So that's good. So what is resurgence in the very basic form? And again, I should also make a disclaimer that this talk is mostly intended for young researchers. So experts probably won't take away anything from it, and I apologize for that. This is rather elementary overview, and of course, there are many technical details and other details that I'm skipping, trying to make it more accessible for younger participants. So resurgence, just like I said a minute ago, is a technique. So we should look at it as a method. It's not some specific class of problems. It's not standard model. It's not Hubbard model that describes only particular class of phenomena. Rather, it's a fairly general tool, which again originates in mathematics and mathematical physics with works of Jean Nicole and Voros and others. And for us physicists, this could be an interesting link or bridge between perturbative phenomena and non-perturbative phenomena. So if I want to summarize what resurgence is, it's basically a tool that connects these two regimes, whereby perturbative I may typically mean expansion in the coupling constant and the strong interaction, and non-perturbative would mean phenomena at very strong coupling. So these are two things that we often want to connect in physics. But it may also mean something else, where perturbative means expansion not necessarily in the small coupling like we do in Feynman diagrams, but rather in some other small parameter. It could be temperature, for example. And I'll give you several more examples later on throughout the talk. Now, this field luckily comes with a visual presentation. As they say, a picture is worth 1,000 words. And luckily in this area, in this field, we have very nice way to communicate with each other. So we may be working on different problems and addressing different questions. But at some point, no matter how you're applying resurgent techniques to physics, sooner or later you probably draw the Borel plane and analyze singularities in the Borel plane. So the process of connecting perturbative to non-perturbative physics using resurgence at very basic level can be broken into 3 parts. So we start with perturbative answer or expression, then represented, and this is where a visual part comes in, on a Borel plane, and then we can try to extract a non-perturbative answer or non-perturbative physics by looking and analyzing the structure of singularities on the Borel plane. At a slightly more concrete level, here on the bottom of the slide, I show you how this goes. Again, at these 3 steps are broken and at the level of formulae. So H bar throughout my talk will be used for small parameter in which we make this perturbative expansion. And again, H bar can be viewed as a coupling constant, as temperature, or whatever small parameter we have in the problem. Then Borel plane is obtained by thinking about analytic properties of the series where we, roughly speaking, divide the coefficients an, called perturbative coefficients, by n factorial. And we write this new function, new series, which, unlike the perturbative series, may now be convergent and have better convergence properties because we suppressed coefficients quite a bit. So we write this new function in new variable s, which plays the role of the action function if h bar is really the h bar from quantum mechanics or path integral. I'll say a little bit more about this later. And then we try to reproduce the non-perturbative completion of the perturbative series on the left by inverse Laplace transform, or Mellin transform, as it's sometimes called in number theory, by integrating this function on the Borel plane along one of the rays. And this is where variable h bar appears back again. And by construction, this inverse transform is guaranteed to reproduce perturbative series, but it also may have much better behavior and actually give you a function that allows to take h bar to some finite values. It contains this exponential suppressed asymptotics and other phenomena. So it may have much better domain than the perturbative series, and perturbative series may not even have much of a domain if it's only formal, very divergent series. So in particular, you can see that if there is a pole that can contribute to the integral on the right side, then the residue of the pole will determine the coefficient. That's basically going to be the Stokes coefficient. And the position of the pole on this Borel plane is going to determine the exponent. That's why I like to think about Borel plane as a plane where action S takes its values. Now, this technique, as I say, resurgence is a tool, it's a technique, so it can be applied in many places. And it's very good at extracting this, identifying the small exponential subdominant behavior. And there are many different applications. For instance, this is the paper that inspired me personally to study dynamical systems. It can tell you how bifurcations happen in dynamical systems. So here is a paper by Sir Michael Berry, where he indeed connects non-local bifurcations to presence, appearance of disappearance of such exponential contributions in resurgent type analysis. And what got me excited, or what I find most exciting about this connection or application to dynamical systems, is that the bifurcations, the changes that happen in dynamical systems are so-called non-local. In the previous talk by John, we saw an example of a saddle node bifurcation. That's a bifurcation where several critical points, stationary points of dynamical system, collide. But so they're characterized as local because this transition happens in a local region in phase space of the dynamical system. But somewhat more delicate and interesting are non-local bifurcations where critical points don't even have to come close to one another. So here on this slide, I show you a bifurcation which is called heteroclinic saddle bifurcation. And it's a change of profile of the flow as some parameter here called NF for physics-inspired reason changes. And as a result, the topology of the flow changes dramatically, but these critical points never come close to each other. And if you think about the flow, which starts at a fixed point T1 and tries to go to the right, in one phase, it goes all the way down. In another phase, it goes all the way up. So the eventual long time behavior of this flow line is dramatically different in these two regimes. But what's interesting is that perturbative small time expansion near T1 may be very similar, and the difference between these two different regimes may be hiding only in the exponential terms. So that's precisely what Sir Michael Berry is talking about in the paper that I just mentioned. So, like I say, this gave me inspiration to study dynamical systems, which I didn't even know very well until that point. And there are many more spectacular applications of resurgence in ordinary differential equations, partial differential equations, integrable models, Schrodinger equations of various kinds, quantum mechanics, and so on. And I realized that my job for doing this talk would be much, much easier if I had to focus on these systems. But unfortunately, I was asked specifically to talk about quantum field theory and string theory. And this makes my job a little bit harder. Why? Because quantum field theory consists of infinitely many copies of such systems mentioned on this slide here. And this is going to be one of the key points to reflect on, in particular for future development of resurgence and its application to quantum field theory. So the basic thing that you learn in the first QFT course is that quantum field theory is a collection of infinitely many quantum mechanical systems. For instance, when we write a field as an expansion in terms of creation annihilation operators A and A dagger that are Fourier modes of the expansion with respect to spatial coordinates x, or we do the same for fermions, our operators A, B, and D on this slide may depend on various Lorentz quantum numbers, but most importantly, they depend on momentum k. And quantum field theoretic systems are characterized by the fact that there are infinitely many values of k to worry about. If we're in non-compact space, there is a whole continuum of k's. Even if we're in a finite box, there are infinitely many discrete values of k. And it is this infinity which actually is responsible for divergence of Feynman diagrams, because when we compute Feynman diagrams, we try to sum or integrate over this momenta k, and that's what's causing infinities and divergences. And this is also what's responsible for the coolest things which happen in quantum field theory, which make quantum field theory distinct from quantum mechanics. Namely, that field theory can change its behavior qualitatively from high energy regimes to low energy regimes, as that happens, for example, in quantum chromodynamics or in strongly coupled condensed matter systems. So therefore, one lesson from this slide is that we have to think about resurgence in quantum field theory, roughly speaking, as infinitely many copies of that in quantum mechanics. And that's part of the reason why my job is not so easy. Well, string theory is one level harder. string theory not only has infinitely many quantum mechanical systems as any single field in quantum field theory has, it actually has infinitely many fields. So in string theory, this is also very important. And we know this even from low energy approximation to string theory, which is usually supergravity plus massive modes. The picture looks roughly like this. In any type of critical or non-critical string theory, the massless fields usually include the metric, the graviton, some tensor fields such as bu mu nu and Ramon fields in type 2a or type 2b string theory. Then dilaton is a massless scalar in heterotic string, and type 1 string we would also have various gauge fields in 10 dimensions. And then on top of it, the spectrum continues and has many more fields, even of higher spin, at higher and higher mass levels. So overall, we get very fast growing spectrum of fields, totally infinitely many of them, which is responsible for cool phenomena that string theory has to offer. Namely, we know that it sometimes plays jokes on our mind in regards of space-time and produces interesting phenomena where spaces of very small size turn out to be equivalent to spaces of very large size. So this can happen only because we have infinite spectrum of fields. Hagedorn phase transition and many other phenomena in string theory are also attributed due to this infinite fast-growing spectrum of quantum fields. So not only we have infinitely many quantum mechanical systems, we have infinitely many fields in string theory. And that's therefore it's a system one level higher. So here we face our first serious challenge as far as applying resurgence to quantum field theory. Resurgence needs some sort of perturbative expansion as a starting point, or to make it quantitative tool. So when I described or gave a definition of resurgence, I think I should have emphasized more, it was on my slide, that it's a very quantitative tool, and this is our strength of this bridge between resurgence and quantum field theory, but it also may come as a weakness, especially if quantitative computations are very hard to make. And indeed, Feynman diagrams are notoriously hard to compute in theories which live in fairly high dimension, even, for example, in typical gauge theories that we would like to understand and solve in dimension 4. The computation of Feynman diagrams is certainly possible, but this is how the answer looks. And you can see many details of such type of calculations from very beautiful talks by Zvi Byrne, Lance Dixon, and others, where result is basically that even with the best techniques that we currently have for perturbative calculations, we can go up to maybe 5 or 7 loop order if we're lucky in some quantum field theories, but usually it's really hard to obtain for example, 10 loop or 20 loop answer, unless the system has some hidden symmetry or, roughly speaking, is integrable. So the first challenge, therefore, is that the sources for perturbative computations, precisely because quantum field theory is infinitely many quantum mechanical systems, are not so easy. So that's part of the difficulty. If I were to summarize quantum field theories on one slide, it would probably look something like this. I would try to organize quantum field theories by their dimension, the space-time dimension. And quantum field theory in dimension 1 is basically quantum mechanics. And as we discussed before, this is where resurgence has many spectacular applications. But my job is to ask what about quantum field theories in high dimensions. And maybe just to comment on it very briefly, if we go to the other extreme to 0 dimensions, even below quantum mechanics, then there is not only no space, but also no time. So we're talking about regular integrals, which also have many interesting applications. For example, matrix models and various finite dimensional integrals that you'll see later in the talk reside here in 0-dimensional QFT slot. But most of my focus, of course, is going to be on dimensions 2 and above. And another thing I want to notice or point out here is that as we go to higher dimensional QFTs, quantum field theories become harder and harder. In particular, it is believed that no non-trivial interacting quantum field theory without gravity can exist in dimension above 6. So there is an actually upper limit which happens very quickly. So complexity of QFT is progressing very fast as we go from 2 up to 6. And also, as illustrated here, one of the basic questions in QFT is often how many interacting terms you can add without running into trouble. Here, by running into trouble, I mean renormalizable interactions. And in the case of scalar field, the answer illustrates this complexity growth with dimension very well. In dimension 2, you can have any monomial added to your Lagrangian, any phi to the n, and theory is nice and well defined. There is no issue. In dimension 3, you get a limit, and it's bounded by power phi to the 6. In dimension 4, phi to the 4. In dimension 5 and 6, phi cube. So these are only renormalizable scalar interactions. Also goes along with this is the fact that as we go to lower dimensions, as you can see, things get easier. And indeed, as we approach quantum mechanics, namely in dimension 2, the slot just one above it, we have many phenomena which make quantum field theories integrable quite often, both in conformal massless regime and in massive regime. So integrability and infinite symmetries are present here. Gauge fields are also easier in 2 dimensions because if you remember from QFT course, massless vector field in d dimensions has d-2 propagating degrees of freedom or polarizations, and when d is equal to 2, it basically has no dynamics, which makes working with gauge fields in 2 dimensions also quite a bit easier for this reason. So indeed, in dimension 2, there are many important developments. Again, here, please don't jump at me. I'm not trying to be fully inclusive. These are just some of the highlights of developments in 2-dimensional quantum field theories, mainly with a focus on gauge theories and other things that are important for their large symmetries. So the simplest quantum field theory with gauge fields in 2 dimensions, namely quantum electrodynamics, already has a behavior which is typical of QCD, namely it confines. So we're in low enough dimension that even electrons get confined. So a bit later, 't Hooft offered very nice solution to quantum chromodynamics in 2 dimensions with one flavor of massive quarks. Bosonization is another cool phenomenon that in field of quantum field theory was pioneered by Coleman and Mandelstam, and there are many others who contributed, especially there was analogous development in condensed matter physics, which allows to turn bosons into fermions. So in dimension 2, even the notion of spin is not so well defined, so that bosons and fermions don't really have clear identity and can be interchanged one to another. So string theory came about in early 80s, as well as realization that or better understanding of infinite symmetries, such as conformal symmetry, Virasoro algebra, and Kac-Moody algebra in the context of conformal field theories. And many other non-abelian interacting quantum field theories with various amounts of supersymmetry were understood in the 90s and early 2000s. So there is quite a bit that we understand. So indeed, as we go up in dimension, gauge interactions become, first of all, more physical. Now they have propagating degrees of freedom starting in dimension 3. And if we go even further high up in dimension, we can also introduce tensor fields, which also wouldn't have propagating degrees of freedom if we're in low enough dimension, but theories in dimension 5 and 6 are often characterized by the fact that they involve or can be represented in terms of not only gauge fields, but tensor fields. So this again illustrates that complexity goes up as dimension increases. And this presents several other challenges of applying resurgence in QFT, which I want to put in a positive way and present them as opportunities for future direction. So these are things which make it a little hard at the moment, but definitely is something that can be and should be understood in the future development. We usually motivate application of resurgence in quantum field theory as a way of trying to define the path integral, this same integral we saw before, where you can try to express the integration contour in terms of Lefschetz symbols which originate at critical points. So Borel plane and the integral on the half line that we saw earlier is basically a projection of such a Lefschetz symbol on just one complex plane from infinite dimensional space of fields. So the first challenge here is that the integral up above is in the infinite dimensional space, and of course this is no surprise. That's what makes mathematical definitions of quantum field theory and many other things that I mentioned earlier not so easy. Another point I want to mention here, challenge number 2, is that if we talk about gauge fields, which are ubiquitous in dimension above 2, then the saddle points of this infinite dimensional Feynman path integral are always degenerate. And the reason is that when we talk about gauge fields, we think about integration measure as integration over all possible values of the gauge field divided by a huge group. It's an infinite dimensional group of gauge transformations. And therefore, if we find a solution such that A equals to 0, in the phase space and the configuration space, it's extremely singular point because this is basically a point divided by infinite dimensional group. So mathematicians would like to use language of stacks perhaps to describe this type of phenomena. And solutions where gauge field vanishes is typically a solution that's always allowed. So our equations of motion often have the form of Maxwell equations, perhaps with some matter sources, or Young-Mills equations, and solution that is obtained by setting gauge field to 0 and other fields to 0 is often the solution. Even if we try to look for non-trivial boundary conditions, if you work in systems with periodicity, put system in a box or in a circle or in a torus, then even with twisted boundary conditions, unless there is no element in the gauge group which leaves our solution invariant, it's still going to be such degenerate or reducible saddle point from the viewpoint of Picard-Lefschetz theory. And also related to these identifications, what happens is that denominator, namely dividing by these gauge symmetries, makes the space of fields in this infinite dimensional integral topologically non-trivial. For instance, it can be non-simply connected, and as a result, the action functional should be thought of as periodic circle-valued Morse function, or maybe something potentially even more complicated. So as a result, you can encounter many interesting phenomena which are very strange and peculiar from the Picard-Lefschetz theory. First of all, you may have Lefschetz symbols and Stokes phenomena associated with critical points of slightly different nature, one of which is Gaussian. That's the kind of critical point we usually like. But then there are always these non-Gaussian points, and this affects how Stokes phenomena happen. So in particular, the Lefschetz symbol associated to Gaussian fixed point can get attached or have non-trivial Stokes phenomenon contribution to non-Gaussian point, but not the other way around. So this directionality kicks in. But this is a phenomenon that can be seen and modeled already in finite dimensional systems, in particular in trigonometric integrable systems. So this can happen. And this is, again, good opportunity for flexing our muscles, trying to understand better such phenomena in the context of QFT, where they're unavoidable. Another thing that can happen is that infinitely many of these Lefschetz symbols undergo Stokes phenomena at the same time. And then if you're trying to add their contributions, or for example, Stokes coefficients, one can run in a situation where you're basically summing same contribution over and over again infinitely many times. And as we know, for example, from summing 1 plus 2 plus 3 plus 4 and so on, which is a zeta function, the result may be non-integer. And this is actually one of the opportunities or I would say benefits that resurgence can offer, because it's hard to think about infinite collection of homological cycles undergoing some Picard-Lefschetz monodromy, but it's much easier to think about numbers such as residues on the Borel plane. It's much easier to think about how infinite sum of numbers can produce non-integer from integer, for example. And speaking of opportunities, so phenomena in topology where Morse function, or we should think about it as action function, is non-single valued, have been studied extensively by Novikov and his followers. So this is the paper from late 70s where he talks about multi-valued Morse function. In fact, he's applying this to finite and infinite dimensional manifolds. And this is a very interesting subject, which gave birth to very delicate phenomena in analysis, such as Novikov rings and techniques which are heavily used in symplectic geometry these days. But many of them haven't made it to quantum field theory or string theory yet, as far as physics goes. So coming back to the slide, I showed you quite a few challenges, which again, I want to view as opportunities or things to keep in mind for perhaps future development. And what we can do is try to start with quantum field theory in dimension above 2, where it's really non-trivial, and try to focus on some sector of the theory. So one sector could be topological, trying to make QFT topological. And even if you do it to simplest possible theory, such as Young-Mills in 4 dimensions, what happens is it becomes basically a quantum mechanical system. So its a spectrum, for example, on a 3-sphere is going to be finitely many, namely the number will be equal to the rank of the gauge group, spectra of harmonic oscillator. So we're back to quantum mechanical system, and we can quickly celebrate that it becomes very tractable. Similarly, in supersymmetric context, there are various localization techniques which can remove much of the space-time and localize everything back to finite dimensional integrals. So we're taking a slide all the way to 0-dimensional QFT. So there are such tools in dimension above 2, and we should think about them rather carefully in the sense that they take us back to familiar territory, but every time we apply such tools, we have to ask ourselves how much of QFT nature these tools really capture, or are they simply just studies in this low-dimensional context. So it seems that we're facing a fairly tall order that we want to understand or better yet make contribution to areas in QFT where exact answer is not known, but we also need a good control over perturbative series. And if you think about systems in dimension above 2, based on what I just said, it doesn't sound, it sounds quite challenging. But I still have some time, and since we started late, I actually plan to use at least 15 minutes if it's okay. And there are many developments which still found good opportunities to apply resurgence, even despite this seemingly conflicting issues that we have to have a good control over perturbative series, but yet the exact answer is not known. Actually, if you think about this phrase, it's not negative at all. It means that what resurgence is really good of is filling the gap and providing answer to theories where non-perturbative definition was not known. And there are at least 2 such systems where perturbative control was amazing by early 2000s, but non-perturbative definition was lacking. And this illustrates another reason why I focused on development starting in 2010, roughly speaking, because in various areas, such as these two that I mentioned here on the slide, in 90s, many techniques were developed to produce exact perturbative calculations in topological strings. So first, starting with work of Kontsevich and Manin using equivariant techniques and localization, then physics development such as topological vertex, relation to matrix models, and many, many other tools provided amazing opportunity for perturbative calculation on topological strings by early 2000s. And natural question came up, how do we define topological strings non-perturbatively? And the history is very similar in regards of Chern-Simons theory with non-compact gauge group. When the gauge group is compact, it's famously addressed in work of Witten from 1989. But when gauge group is non-compact, a famous example or prominent example is SL2C, so-called complex or analytically continuous Chern-Simons. The Hilbert space is infinite dimensional, and even though theory is topological, it's facing many of the challenges that I mentioned earlier. In its path integral in 3 dimensions, which has gauge fields and some of the features that I described on the previous slide. And again, perturbative techniques to great accuracy, basically all ordering perturbation theory were developed in early 2000s, and natural question came about how to define it non-perturbatively. So resurgence is very good in addressing this kind of physical problems where we have really good control over perturbative series, but non-perturbative definition is lacking. And these were 2 obvious opportunities where many people contributed, and I've mentioned some of them on the previous slide. So I'll give you one challenge. I don't want to make an impression that despite many, many works that are listed here, the subject is finished. Again, this is mostly for young people to motivate you to think about these topics, and I encourage you to talk to various people who contributed to these developments. And here is a simple example. Since I personally worked on Chern-Simons theory a little bit more, I focus on this example. This is a perturbative series shown on top of the slide, and the bottom of the slide gives you a method how it's obtained, and there are many, many other examples to which I don't know non-perturbative completion. So in other words, this is an example where you can compute coefficients, these perturbative coefficients to any desired order. There is no question about it, but non-perturbative answer is not known. And I want to maybe make a quick remark that don't let the expression on the bottom of the slide to fool you. If even though it's written in terms of Q, it's actually still just a perturbative series. It's not a well-defined function. So one thing that I hope is clear by now, as far as application of resurgence in quantum field theory and in string theory, is that it's, and that's a good thing, it's interdisciplinary interaction. It requires some input from that field to which it's applied, such as perturbative series or some insight. And what resurgence is really good about is at taking that input and making it, improving it, taking it one notch up. For example, it can take something which has perturbative definition and try to help us find non-perturbative definition, and so on. So, of course, computation of Feynman diagrams could make sense just in quantum field theory by itself, and study of exponentially suppressed contributions can be studied just within analysis and resurgence by itself. But when we talk about these applications, we really need both interact closely one with another. And in the remaining time, as promised, I'll give you a few examples where such interaction happened, and it brought fantastic results, even in this short time of development, despite all these challenges in quantum field theory and string theory that you would naively face due to various infinities and so on. So I want to organize or suggest that if you're lost with details of each given application, ask yourself at least 3 questions. Or when we want to reflect on where we're going next, we have to think about the following question. One is very simple. What is the small parameter? Namely, what is this parameter that I call h bar? This basically is a question about perturbative series. The second question is where the perturbative series is coming from. So this is something that resurgence will improve on. Namely, it will take this as an input. It is going to be a fuel for resurgent analysis, and it will do something good to it. And then once the dust is settled, when the problem is solved, we have to ask ourselves, okay, where else can we apply this? In which areas, which models can we solve using these insights or techniques? So what are the lessons that we learn from this? These are basic questions. So H-bar can be many different things, and in the remaining few minutes, I'll show you what it can be and then application. So one simple one is where it's actually 1/n. There are many physical problems where integer number n is the number of either colors or flavors, and it can be describing size of the matrices and matrix models, but again, we're talking about QFT. So natural expansion that often is possible is in the limit where n is large. So either number of colors or flavors goes to infinity. So in that case, if you have a technique to produce perturbative 1/n expansion, you can think about behavior in n and what a Borel plane is telling you. And very often, it's telling you something about non-analyticity in n, or where phase boundaries as you change value of n can happen. And if I focus on opportunities, I think this is a great opportunity for identifying conformal windows for which we often don't know the lower limit. For instance, in 4-dimensional gauge theory, such as QCD, we don't actually know exact value of n at which a conformal window ends. And this is perhaps a resurgence can help to solve this kind of problem in the future. So this example shown on the slide comes from supersymmetric localization, illustrating yet another thing that I said earlier, where integral can be made finite dimensional using supersymmetric technique. And in the case of 3-dimensional supersymmetric QCD, that's the 1-dimensional integral that you get. That's fairly simple. So another interesting application, which was pioneered by Heller and Spolinsky, was in the case where h-bar, the small parameter is time, or more precisely time measured in the units of inverse temperature. And in this case, this example is very similar to example of dynamical system that I mentioned earlier. So we're talking about evolution of the system, and we're trying to predict what's going to happen at later times. For example, find possible attractors and long-term behavior from perturbative behavior. So here, the technique that they used is based on Müller-Israel-Stewart evolution equation, which is basically a relativistic version of Navier-Stokes equation. It describes fluid mechanics in viscous regime in 4-dimensional Minkowski space, so it's fully relativistic. And these partial differential equations can produce for you a version of a dynamical system where, with the help of resurgence, so here is the Borel plane, that's the visual picture that I advertised before, you can predict many interesting phenomena such as, again, attractors, non-hydrodynamic modes, and so on. This is an interesting application because it makes contact with holography very closely. So various applications to, say, quark gluon plasma and other relativistic fluids can be realized holographically, where these non-hydrodynamic modes are close cousins of quasi-normal modes for black hole physics. So this is very interdisciplinary in the sense that it involves gravity, and some of these singularities in the Borel plane can be understood geometrically in this holographic regime. So by now, this is, again, fairly broad line of development. So Another application which also has close contacts with holography and in a completely different realm is application to conformal field theories, where h bar is again a coupling constant. So I'm returning to the case where it's coupling constant. And there were two papers which appeared almost simultaneously, mentioned here on the slide, the first two, which try to compute cusp anomalous dimensions in four-dimensional superring mills. And this is again a kind of problem where resurgence, so to say, fills the gap in ideal way. Because here in this development, there is a nice equation that reduces cusp anomalous dimension to integrable system, basically by Bizart, Eden, and Staudacher. And it's a version of thermodynamic beta ansatz that can be nicely solved in different regimes at weak coupling and strong coupling. But interpolation, which is shown here on the slide, is beautifully performed by resurgent technique and is exactly this kind of non-perturbative extrapolation that we cannot get easily by other methods. In this context, what it tells us is the anomalous dimension of a Wilson loop with a light-like cusp, as shown on the left figure of the slide. It has many other incarnations, for example, in terms of divergences of gluon scattering in this theory, or you can formulate it equivalently in terms of conformal dimension of the operator, such as phi derivative to some high power phi, where this number of derivatives is basically the spin-off operator, and such operators of large spin and twist equal to 2 have anomalous dimension which is very close to spin, but the difference due to logarithmic term is again controlled by the same function of the coupling constant. That's the cusp anomalous dimension. So another application where h bar is a coupling constant, and in fact, as you can see, this is perhaps the largest in terms of number of references I mentioned, and this is indeed the one which started it all. So even if Misha didn't make this comment earlier in the talk, I would certainly emphasize it here, is to gauge theories and their cousins in dimensions 2, 4, and their analogs on quantum mechanics. So here, the number of outcomes of application of resurgence is enormous. It's by far the largest. But I want to focus on one particular outcome of this development, where many different types of non-perturbative behavior are attributed to new classical field configurations. So as I mentioned earlier, it's really hard to have exact perturbative series in gauge theory above dimension 2. That's quite challenging, and I hope that we're gonna get that day, and clearly when the day comes, we'll have no trouble applying resurgence and getting many nice results, exact results in that area. But before that happens, we can actually try to approach the problem from both ends. We can try to anticipate what should happen in high dimensional gauge theories, first of all, by exploring interesting saddle points and also taking the lessons from two-dimensional theories and from quantum mechanical systems. And here, such classical or semi-classical field configurations play a very important role. They basically provide these saddles for potential poles on the Borel plane and saddles for Feynman path integral. And at some point, I thought of classifying all of them for you because there are so many. I decided that it's probably impossible, and I suggest that in this program, there will be a talk devoted just on classification of these interesting classical field configurations. They're called bions, fractons, unitons, and so on. I have to point out that fractons is referring to the name of soliton, not to the name of condensed matter phenomena with restricted mobility, which is very popular these days. So here a fracton refers to soliton solution. Then even other terms actually sometimes have other meanings. For instance, bion happens to be also name of a person who worked in not so unrelated area. So like I said, I did my homework and searched many references even beyond the ones which mention resurgence explicitly, and in area of mathematical physics, this is one of the last names that comes up and is not terribly relevant. Also, baryon are used as solitons sometimes to describe solutions to Born infield equations or action. And in that case, they're also naturally referred as baryons, where BI stands for Born and infield. And I even managed to find that there are products online that you can order with the same name. So once you do the search, don't get confused. But coming back to physics, I think there are enormous opportunities here, in part because many of the solutions are non-BPS. And in that case, there is, again, enormous opportunity of trying to understand and study them better. So here is a good example or illustration. So take two instantons. We know that one instanton is a solution to anti-self-duality equation. So anti-instanton would be a solution to self-duality equation, and both of them naturally solve Young-Mills equation, or at least if they're widely separated. So there are many solutions of this kind that don't solve first-order partial differential equations, but solve second-order equation of motion, such as Maxwell equation or Young-Mills equation. And I showed you example of it on an earlier slide. So many people, and I learned this from Michael Adi, try to describe solutions of this kind from various perspectives. For example, moduli space of solutions for a single instanton is finite dimensional, and this finite dimensional space can be understood, for example, as space of holomorphic line bundles over twistor space. But natural question is, what about such systems which don't solve anti-self-duality equation, but only obey Young-Mills equation? So again, many people have thought about it, and this goes back to late 70s, and there are many different proposals. For instance, at some point I've heard from Sir Michael that if you consider not just holomorphic bundles over twistor space, but all possible bundles with perhaps certain condition, this would be, of course, infinite dimensional set. That would be the right framework to describe such non-supersymmetric solitons and nice solutions. So question here, or opportunity for the future, is to apply Penrose-Ward transform to baryons, fractons, and many other things that I mentioned. Recently, a framework based on ambitwistor space got a lot of traction, and maybe one should think not about twistor space, but rather about ambitwistor space. In fact, original motivation for ambitwistor space was precisely to incorporate not just self-dual, but also anti-self-dual configurations and put both of them on the same footing. So as far as I know, not much has been done in this direction. And that's definitely one of the opportunities for the future. The way this solitons are used in the works I mentioned is often to say something about physics. And here I want to make a simple illustration based on idea that goes back to 't Hooft, that in the familiar background of instanton, that's solution to self-duality equations, helicity or axial charge are not conserved. So we usually learn this from perturbative anomalies, for example, the one which relates axial current to trace F wedge F. If we have a classical solution that carries a total charge with respect to integral of trace F wedge F, then basically it means that this current won't be conserved, or that a quantum number can be changed. Similarly, so this offers an opportunity, and indeed this kind of research is already in the papers I mentioned, or at least there is a beginning of this research, to think about charges of many of these objects with respect to more delicate quantum numbers. So recently, understanding of quantum field theories was ameliorated by a lot of work on discrete higher form and higher group symmetries. And because they're discrete, they're usually harder to capture, something like charges of non-BPS objects in string theory and quantum field theory. And therefore, it's natural to ask, what are the charges, in particular with respect to these discrete higher form or higher group symmetries, that such classical field configurations carry? And this would also help to the previous question, where this BPS type bounds are really hard to find and probably in the simplest form don't even exist for many of these non-supersymmetric solutions. But these more delicate charges can be very important. And if you think about it, this is actually very natural, because in the context of string theory, this is exactly what happened. Non-BPS solutions, which are close cousins of baryons and fractons, have been realized to carry charges under discrete symmetry, under discrete groups, such as cobordism groups and K-theory charges in a non-supersymmetric setting. And this goes back to work of Sen, Witten, Majumdar, and Sen in late 90s. So they studied non-supersymmetric configurations, which realize non-supersymmetric king solutions as brain anti-brain systems. So here on the picture, I illustrate a phase transition where on a circle, this is very similar to circle compactification of four-dimensional gauge theory with a twisted boundary condition. So Sen considered a Z2 twist. You can have, yeah.
Sorry to interrupt. How much time do you need more?
I think I have 2 more slides, so maybe a couple of minutes, almost done. But I definitely wanted to go over this because
it's be quite a bit.
Yeah, sorry, we started a bit late, and also there were a couple of questions in the beginning or comments. I hope it's okay. So what these people did, they studied how, for example, in a circle, one soliton can bifurcate into 2 different solitons or vice versa. So for instance, we can start with 2D brains, one brain and one anti-brain wrapped on a circle, and when size of the circle is small, that's a good description. But if you consider the system on a large circle, a more stable configuration, and again, it's non-BPS, non-supersymmetric, is just a single kink, and it exists in this case because of the twisted boundary conditions. And from string theory point of view, this phenomenon can be understood as tachyon condensation, where the twisted boundary conditions on a circle project out the lowest tachyon mode, but the first non-trivial tachyon mode here with n equals 1 becomes massless for a certain value of the radius, and that's what triggers this type of behavior, which is again very similar to behavior of such classical field configurations in gauge theories that perhaps may have realization or even connection to non-BPS objects in field theory. So here is another example where h bar is coupling constant. It's a non-relativistic Fermi system. I think I'll skip this slide in interest of time, since indeed I'm running late, and just want to point out that here there was not just one work, but many papers by Marcos Marinia and Thomas Rice, where not only they applied it to non-relativistic many-body fermion systems, but they turned some of this resurgence logics around, and even in cases where we cannot compute perturbative series exactly, by very good understanding of what non-perturbative physics is, in this case, the mass gap for superconductors, one can actually predict, and in their cases, carefully check that perturbative series does have the right behavior. And I want to conclude with this slide where h bar is yet something else. It's expansion in 1 over the charge. So charge can be large, just like number of flavors or number of colors that we discussed before. And I want to point out that this is a very natural idea, of course, and only recently it was really explored fully by Dondi, Kaligarikis, and Orlando and Riefert. And there was another closely related paper by Simeon Hellerman just yesterday. So this group of people already have been working on large charge behavior in quantum field theories, in particular in conformal field theories. And they produced a lot of very powerful, strong results where, again, resurgence is a perfect tool to come in and make a significant improvement, in part because it's exactly the kind of situation where you can compute perturbative type of expansion, in this case, in 1 over the charge, to very good accuracy, and resurgence can come and fill many gaps that you cannot address otherwise. So here in this paper, they apply it to 3-dimensional theory, so it's above dimension above 2. So it's a 3-dimensional ON model, which we don't know how to solve exactly, but using this technique of resurgence and interpolation, very similar to example of cusp anomalous dimension that I mentioned earlier, they obtain amazing agreement between different expansions up to roughly 10 orders of magnitude. So I want to conclude by saying that I try to focus on a period which is perhaps one of the most fruitful for interaction of resurgence with quantum field theory and string theory. And as you can see, there are many challenges for many good reasons, but this is good. It means that there are many more opportunities for us in the future. And already a lot of spectacular results have been done, and I hope I gave you a flavor of what they are. In particular, we clearly see upsloping derivative and trajectory going up. So this is a good opportunity for many young people to come and produce many more results that will be home runs in this area. Thank you. And sorry for running over time.
Okay, let us thank Sergei for an interesting review. Okay, now let's see if there are questions. So I see a raised hand from David. If you have a question, please go ahead.
So thank you very much for this overview. You raised 3 questions and concentrated mainly on the first one, and that is what is H bar. But the second question is interesting to me. Where does the expansion come from when the expansion is in the coupling constant? It need not does come from Feynman diagrams, from nonlinear renormalized Dyson-Schwinger equations. One contain very interesting examples of resurgence, and one of those ought to have shown up in your literature search, because Mishi Borinsky and Gerald Dunn have solved a 20-year-old problem which I raised in the resurgence community 10 years ago at David Savon's conference in Pisa, where we found the perturbative solutions to an indefinite number of loops for phi cubed in 6 dimensions, the largest dimension you talked about. And those authors have shown spectacular examples of resurgence of our perturbative expansion around non-trivial instantons. So that gap in your talk about where does it come from, expansion and coupling constant, doesn't just mean Feynman diagrams. Think of Dyson-Schwinger equations.
Yes, thank you very much. I completely agree with the comment and want to clarify that you actually showed several examples where this perturbative expansion is coming from. And of course, I cannot review infinitely many of them, but some that were mentioned that not always come from Feynman diagrams. For instance, in the context of this hydrodynamics, it actually doesn't come from Feynman diagrams. It doesn't come from Schwinger-Dyson equation. It comes from this MIS theory of fluid mechanics. And in the case of cusp anomalous dimensions, it comes from this Bizard-Eidenstein-Daher equation. So I tried to make comment along the way, what was the origin of this small perturbative series, trying to give a flavor that indeed it's not always Feynman diagrams. In many cases, it's something else. Quite often, it's related to thermodynamics beta-ansatz equation in one form or the other. And yeah, I completely agree with you that it could be a Schwinger-Dyson equation as well. So again, I want to emphasize that my time was limited, and as you can see, even data abused. So some examples I was able to mention, and of course there are many, many more. So not to say that they are less important or don't exist.
Thank you.
Any other questions? Okay, since we are a bit late, so let us thank Sergei again for an interesting review.